or circuits. The purpose is to predict the behavior of circuits containing resistors in series and in parallel, examine the behavior of ohmic resistors and capacitors, use multimeters to measure experimental values of conventional current and potential differences, and finally to compare experimental values to calculated values. The preview of the findings is shown below. The node rule: the current entering a junction will equal the sum of currents from each junction. Loop rule: the difference in potential for a round-trip path is zero. Capacitance measures how much charge can be stored in a capacitor for each unit of potential difference, is equivalent to the quotient of the charge Q on one of the plates and the absolute value of the potential difference V, also equal to the product of vacuum permittivity and the area of one plate divided by the separation distance of the plates. The formulas relating to these ideas are shown on the screen. And finally, we also have electrical resistance, which is the resistance in any component is equivalent to Ohm's law, assuming the resistance is constant. When resistance are in parallel, the equivalent resistance of the resistors equals the following. And then when the resistors are in series, the equivalent resistance of the resistors equals the following. As we discussed in the introduction, the main physics ideas are node rule, loop rule, and electrical resistance. Below are more figures that relate to these ideas. One assumption we had was that the resistance for both the ammeter and wire is negligible, and the reasoning for the models is that both PHYS and physical models are shown for the clarity of the results. The system is the ammeter or voltmeter, and the surroundings is the circuit. The pictures taken during lab are shown on the screen. Part 1. A simple circuit. Construct a circuit that consists of two batteries, two resistors, and ammeters. The predicted current is 0.0204 A, the actual current was 0.02 A, and the reversed ammeter is negative 0.02 A. Open circuit. Same as the one in part 1, but we replace the second ammeter with a voltmeter. The predicted and experimental values match. Part 3. Potential differences. Close the circuit from part 2 with the wire. Measure the potential difference between the points shown in the diagram. And the potential differences are listed below. And the loop rule is 3V minus 0.96V minus negative 2.04V equals 0V. Part 4. Ammeter in parallel. Reconstruct a circuit such that an ammeter is in parallel with a 100 ohm resistor. The current measured by ammeters increased from 0.02A to 0.06A, and we can also use mathematical methods to confirm the findings. Part 5. Calculating resistance. Calculate the resistance of the resistors, ammeter, and wire based on the experimental values. Part 6. RC circuit. Construct a RC circuit. Measure the time to charge the capacitor and the time to discharge the capacitor. Repeat with the 20 ohm resistor. The results are shown on the screen below. Part 7. Time dependent voltage. Construct an RC circuit. Charge the capacitor and note the potential difference across the capacitor. Remove the battery and pause the circuit in the PHYS simulation. For every circuit, record the potential difference across the capacitor as the capacitor discharges. Record the potential difference for 20 seconds. Plot ln V over V0 versus time. Using the equation below, the slope of the plot equals negative 1 over RC. Solve for RC, which is a time constant. The slope was negative 0.17112, and if we use this value to solve for RC, we get RC to be 5.8411 S. The graph using these calculations and data is shown on the right. Some observations we made was the calculated resistance values are greater than the actual resistance of the resistors in the PHYS simulation. An explanation for error would be the precision of the ammeter, rounding during calculations, and timing error when determining the charge and discharge times for the RC unit. A true ammeter has non-zero resistance. Wires have some non-zero resistance. This would have reduced the current in the circuit slightly. Current readings would be altered, so there would be lower current measurements on the ammeter. The ideal model predicts that the capacitor will attain full charge practically instantly. This prediction would not come true in actual life. Wires would have non-zero resistance, increasing the time it took for the capacitor to charge completely.